Hey there, AP Environmental Science class. We're going to move on to Chapter 2 now, Science, Matter, Energy, and Systems. Once again, I'm going to break the lecture down into two parts just to make it a little bit more manageable for me and a little bit more manageable for you. Now, what I'll say is as we go through this chapter, a lot of this is going to be review for you guys. We're going to talk a little bit about the scientific method. We're going to review a little bit of chemistry. We're going to talk a little bit about the first and second law of thermodynamics. So again, I know a lot of you guys, if not all of you, have heard of all this stuff. But again, I think it's good just to review, just to make sure we have the foundation nice and solid for us. And then finally, come Chapter 3, we'll really begin to dive into the real crust of this course, this AP Environmental Science course. All right, so just bear with me for these lessons here. So let's start going, and I will move on to the first slide. So there's a case study that starts off this chapter, talks about how scientists learn about nature. It's basically experimenting with a forest. It's the Hubbard Brook Experimental Forest in New Hampshire. What they did was they wanted to see how soil and water nutrients changed when you basically deforest or cause deforestation of a forest. So it compared the loss of water and nutrients from an uncut forest, a control site, to one that had been stripped, the experimental site. And what they found was that the stripped site had 30 to 40% more runoff, more dissolved nutrients in the soil and in the water, which isn't necessarily a good thing. We'll talk about that down the road, and more soil erosion. So actually most of the soil, or a lot of it, was actually washed away. And this is kind of a picture. Here was the experimental site. Again, on the right here, where they clear cut the forest near this stream, and then here's the control site where they didn't. And again, they compared one against the other, and that's basically the scientific method, and that's what we're going to talk about. So again, this was the effects of deforestation on the loss of water and soil nutrients. So what do scientists do? Scientists collect data and develop theories, models, and laws about how nature works. Tools of the scientist: observations, okay, either with our senses or through instruments. We take measurements, and then we use experimentation to try to determine what our observations and our measurements are telling us. So here are the steps in the scientific method, and what I find it interesting is that when we look at these steps, they're very similar to the 6 parts of the lab write-up that you have to do for this class, and that you've been doing for AP. Those of you who are in AP Biology or other AP classes, or even just your regular Regents classes, pretty much your lab write-ups follow this scientific method. What are the steps? We identify a problem. We find out what is known about the problem. That's your background information, right? We ask a question to investigate. We then perform an experiment. We collect data. We analyze that data to then answer a question, and then we propose a scientific hypothesis to explain that data. And then we continue. We use that hypothesis to then make a testable projection. We then perform experiments on that test projections, and then we either accept the hypothesis as true, or we revise it if our information isn't, or what we're gathering isn't pointing to our hypothesis. We'll then revise it, and over the course of doing this over and over and over again, we end up developing a model and then a scientific theory. A model is another way to study nature, and a scientific theory is a well-tested and widely accepted hypothesis. Now, scientific theories are always in flux, okay? Many of them are sometimes change because of new instruments or new technology that allows us to find new observations and new measurements which then change the hypothesis. So for instance, a couple of thousand years ago, we thought the Earth was the center of the universe, right? For all the information, all the observation and measurements ancient man or ancient woman had about the stars and the sky, made perfect sense that the Earth was the center of the universe. So that was the theory for thousands of years, until we invented the telescope and then realized, wait a second, that is really not the case. We also threw in some calculus there into some models and realized that, whoa, the Earth is not the center of the universe. In fact, the Earth revolves or goes around the sun, right, orbits the sun. So we had to revise that theory, and that theory ended up changing. So just understand that, okay, in science, and that's what you guys are, maybe many of you budding scientists going to go out into the world always question things, because even though things seem as they are, as we get more technology, as we get more intelligent as a human species, sometimes these hypotheses change. All right, this is just basically a visual of what we just discussed in the past slide. So if you like to look at things visually, definitely take a look at this. Again, this is how scientists collect evidence to learn how nature works. Now, scientists are curious and skeptical, and they demand evidence. So scientific knowledge advances through scientists publishing details of their methods and results, and then other scientists peer reviewing those and saying, hey, I don't think that's right, or yeah, that's really right. And that's how science advances. If we don't do that, if we don't publish methods and results and peer review, then those methods and results, then we're really not doing true science. New data and analysis can lead to revised hypotheses, and that was the example I gave you about the Earth being the center of the universe. We know now that is definitely not the case. So critical thinking and creativity are important in science. You've got to think critically, have a skeptical outlook, evaluate evidence and hypotheses using inputs from a variety of reliable resources or reliable sources. I think that's important. Nowadays, a lot of our inputs are not from reliable sources in science, and that's unfortunately a little bit of an issue right now, at least in my humble opinion. Identify and evaluate personal assumptions, biases, and beliefs to distinguish facts and opinions before coming to a conclusion. Imagination, creativity, and intuition are also vital. So, for instance, so all human beings have biases and personal assumptions, and you really need to take them out when you do science. Why I love science is that, in my view, science should never be political. Science is about facts. Okay, so if you have personal assumptions, you have personal biases, you need to try to take them out of any scientific experiments that you do, because again, you just want facts. And those facts then will lead to a scientific theory, a widely tested and supported by evidence, or a scientific law or a law of nature. So while theories are oftentimes changed throughout time as we gather more or different info, scientific laws or laws of nature are pretty concrete. I'm not saying that they don't change, but they have a harder time of changing. They're well-tested, widely accepted description of what happens repeatedly and in the same way in nature. Think of the law of conservation of matter. Think of the first law of thermodynamics. These are things that we know happen. We're pretty positive they happen. And even as we get more intelligent and more instruments and more technology as human beings, most likely the scientific laws or the laws of nature are not going to change. Science can be reliable, unreliable, and tentative. So reliable science, data, hypotheses, models, theories, and laws widely accepted by experts. Unreliable science are results presented as reliable, but without peer review or having been discredited. This, unfortunately, folks, is what we're getting a lot of in the media right now. We're getting this unreliable science, people just getting up without having been peer reviewed, without having their models and their hypotheses discredited or try to be discredited by peers. They're just going out there and giving their results, and unfortunately, that's not reliable science. Tentative science is preliminary scientific results without adequate testing and peer review. So I would argue right now, these are some of your COVID vaccines, right? A lot of are in the second or third phase. So we're trying to get the adequate testing and the peer review, but we're not there yet. So until we do, I would say that those COVID vaccines are still tentative science. We're trying to get them to be reliable science, and what we don't want them to become is unreliable science, okay? So again, hopefully those are some examples that'll make this a little bit easier for you to understand. Science does have limitations. Scientists cannot prove or disprove anything absolutely. Again, science attempts to establish a high probability, but again, things could change, like Earth being the center of the universe, right? Scientists are not free of their own bias in the hypotheses and results. So again, when you do peer review, or if you get into this in college or maybe as a career, understand if you're reading a peer review from another scientist, that scientist may have some bias in there, and you have to understand that, and you have to try to make sense of that as you peer review someone's data or someone's hypothesis. Systems in the natural world involve many variables and complex interactions, and therefore we use mathematical models and statistical tools to help deal with these. Some mathematical models that you probably hear a lot about are weather forecasts. Meteorologists use computer models to predict where hurricanes are going to go, where snowstorms are going to go, and all those models are their mathematical models. They're formulas that get put into these models. Each different model has a different formula, okay, that has been studied or used by the scientists that develop those models. And that's why that's why you get different weather forecasts from different models, because each model will use a different mathematical model and statistical tool incorporated in its model to help it determine what the future weather is going to be. And again, that's what modeling is all about. Okay, so let's moving on now. What is matter and what happens when it undergoes change? So again, I know you guys know this pretty well, I'm sure, but matter has mass and takes up space. So matter exists in three physical states: a solid, liquid, or gas. Two chemical forms: elements and compounds. Again, I know you guys have heard of this stuff. Elements have unique properties and cannot be broken down chemically into other substances. So that periodic table of the elements that you used in chemistry, okay, all those substances on that chart are elements, okay? They have unique properties and they can't be broken down chemically into any more substances. They are what they are. And again, those are arranged in that chart called the periodic table. Compounds are when two or more different elements are held together in fixed proportions. Okay, so once again, gold and mercury are chemical elements. They have unique properties and they can't be broken down chemically into anything different. So gold is gold, mercury is mercury, and it is what it is. Now, atomic theory: all elements are made up of atoms. Okay. There are subatomic particles in the atom. Nucleus has protons and neutrons. Protons have a positive charge. Neutrons have a negative charge. And of course, orbiting the nucleus, of an atom are the negatively charged electrons. Okay, they're the ones that orbit the nucleus. So here is a example. This is carbon. Okay, has an atomic number of 6 protons, 6 electrons, and also has 6 neutrons. Okay, and now the new atomic theory, as I'm sure you've heard about, is more of a cloud, not necessarily distinct orbits, but more of this kind of orbital cloud that the electrons are in as they go around the nucleus. Each element has a unique atomic number. Okay, that atomic number is the number of protons in the nucleus. Now, there are two numbers, and again, I know you guys are aware of this: the atomic number, which is unique, okay, and the mass number, which is not unique. So the mass number takes into account the number of protons plus the number of neutrons in an element. Now, the number of neutrons can change. So the same element could have different mass numbers. It's still going to be that unique element. An isotope is a form of an element with the same atomic number, but different mass numbers. Now, this is important, and I'm gonna give you one way why this is very important. So apparently, okay, carbon has different isotopes, and the carbon that comes out of volcanoes has a different isotope, it's a different isotope. It has a different mass number than carbon that comes out of factories, out of smokestacks. Okay, they both have different mass numbers. Okay, they're both carbon, but different numbers of neutrons, okay, in the volcanic carbon and the human-made factory carbon. So one of the smoking guns that we are totally, or not, maybe not totally, but 90%, 80%, 90% of the global warming that has occurred in the last 150 years has come from humans. How did they figure that out? Well, some of the people who are maybe on the other side of the climate change fence will say, well, this is just a natural occurrence that's happening right now, that volcanoes are erupting. This is natural carbon like in the past. Well, what scientists did was they went to Antarctica, they took an ice core out, okay? And this ice core obviously goes back millions of years. And they looked a couple of million years ago at the isotope of carbon that was mainly in the atmosphere. And that isotope of carbon that was in the atmosphere was the volcano type of carbon, the carbon that comes out of volcanoes. Then they went up the ice core and they took a look at the last 150 years. And guess what? The carbon in the air, the majority of the carbon in the air is the isotope of carbon that comes out of human-made factories. So that pretty much puts away the argument that it's volcanoes, it's this natural thing. No, it's not. Because the carbon in the air right now is a different isotope, has a different mass number than the carbon that was in the air millions of years ago. Okay, and again, I will show you a video when we get to climate change that that talks about this. And again, that's one of the smoking guns that we've kind of come out of the past couple of years in this climate research. Okay, all right. So what's a molecule? Molecule, combination of two or more atoms of the same or different element held together by chemical bonds. So there are a couple of these bonds we'll talk about. Ions are atom or group of atoms with a net positive or negative electric charge formed when an electron are gained or lost. So if you gain an electron, you have one more than you normally have, well, then you're going to have a negative, okay? You're going to be a negative ion. If you lose an electron, so you have less electrons and more neutrons, well, then, of course, you're going to be a positive ion. And that helps us determine the acidity of substances. Acidity is a measure of the comparative amounts of hydrogen ions, which is H+, and hydroxide ions, which are a negative ion, OH-, in a volume of water solution. We call it by measured with pH. Neutral solution equal to 7. Acidic solution has a pH less than 7, and a basic solution has a pH greater than 7. Okay? So here's just a picture of nitrate loss in a forest. You'll notice up the left side here, nitrate, which is a negative ion, NO3, concentration here along the left. And you'll notice down on the bottom, the x-axis has the year. And you'll notice this was nitrate losses in this forest. This was the experimental forest we looked at in the initial case study. And you'll notice the undisturbed watershed. You saw the nitrogen concentration kind of stayed the same in the soil. But you'll notice the disturbed, or the one where they did the deforestation, look at the concentration of those nitrate ions in the soil. This is not good for soil, okay? We'll talk about that in a couple of chapters. But the point is, these ions are going to be important to us when we discuss the natural nutrient cycling of the earth and of soil, okay? Once again, here's just a kind of a pH scale for you guys, just to kind of see certain basic things that we have around our house. So for instance, vinegar, wine, beer, oranges are rather acidic. They have a pH of 3. Pure water is neutral, so right at 7. You'll notice our blood, slightly basic. Okay, you'll notice household ammonia, rather basic at an 11 or 10.5 to 11.9. You'll notice seawater, slightly basic. So again, you can kind of take a look at this and pick out some basic things that you know about and to see if they are what their pH scale kind of is. All right. Okay, talking about chemical formulas, this shows the number of each type of atom or ion in a compound. So there are two types of compounds: ionic compounds like sodium chloride, salt. Okay, tend to dissolve in water and break into ions. Okay, so ionic compounds are when one substance will give its atom give its electron to another substance, and that'll cause them to kind of come together. Or we have covalent compounds like water, H2O, where the electrons are actually shared between the elements. Okay, so lost my slide here. So once again, here is sodium chloride, your basic table salt. Okay, you have the positive sodium ion, the negative chlorine ion. They come together because the positives and negatives attract. And there you have the compound of table salt. Just some more chemical formulas for you. Okay, here's hydrogen, H2, oxygen, O2. Okay, carbon monoxide, 1 atom of carbon, 1 of oxygen. Sulfur dioxide here, 1 of sulfur, 2 of oxygen, etc., etc. All right. Okay. All right, so organic compounds are the chemicals of life. This is going to be the second part of this lecture. So this is the end of part 1, and I will see you guys in a little bit for part 2.